Thank you all for attending our talk on cyber-informed machine learning. I know it's pretty late in an energetic conference, and I'm sure everybody's ready to kind of wind down and start thinking about the weekend. I know I am. So this cyber-informed machine learning is a framework for explainability when machine learning is used in the SOC, in the Security Operations Center. So I'm Clarence. I'm a senior data scientist at the Software Engineering Institute, and this is my colleague and friend Jeff Mellon, a machine learning research scientist at the Software Engineering Institute. So we are a federally funded research and development center that's operated by Carnegie Mellon University, and our research is at the intersection of cybersecurity, AI, and software engineering. Okay, so we'll just start out with an audience query here. Just by show of hands, or if you want to start yelling, how many people here feel that machine learning has achieved its full potential in the SOC? Okay, that's great, because that's like the whole premise of the presentation. So if you guys had all raised your hands, we'd probably just close up shop and walk out. So how about this? How many people think that machine learning is trusted in the SOC? Okay, yeah, a few more people. Yeah, good. Okay, so the motivation for this talk is the SOC, the Security Operations Center, and let's consider a busy SOC analyst. And Jeff and we are data scientists, but we can appreciate that this word busy is like a tragic understatement for what these people do. The SOC may be fielding 250,000 alerts per day, and all of those need to be triaged, with some combination of automated and manual review. And the alerts that are selected for manual review, the analyst has, on the order of 15 minutes to basically make a decision. Is this a benign event, or is my organization under attack? So this is a lot of pressure, obviously, to put on a person. So in an effort to kind of alleviate this pressure, the SOC management has installed an anomaly detection system. And this system promises to identify novel zero-day threats through the power of machine learning. Okay, so this guy, I think, knows what's about to happen. Does anybody here have a reaction, what's about to happen? Somebody must. Bueller? Yeah, so thinking false alarms, false positives. Basically, this guy is wondering, is this system that is supposed to help us going to somehow increase the burden on us? And so cybersecurity is data rich. We're overwhelmed with data, so it's a natural setting for machine learning. There's tens of thousands of academic papers on using machine learning for cybersecurity, using machine learning in the SOC. When you walk on the vendor floor here at RSA, everybody is promoting some type of AI or machine learning in cyber. Commercial SOC products, they all have machine learning features. So the question that remains is, why is machine learning not yet broadly used and trusted in the SOC? So I'll pass this over to Jeff, but in the meantime, does anybody have any thoughts? Like, why not? Oh yeah, that's a great point. Yes, so machine learning is stochastic in nature, and so you may not get the same result every time you run a prediction. So that creates confusion, and to an end user who may not be a data scientist or familiar with the models, when you're getting inconsistent advice, you're going to start to question, and maybe your trust is going to erode. That's a great point.
That lack of data strategy. I mean, it's a lot of data, but it's cleansing and preprocessing and getting it ready to train a model. That's where all the work is. It's hard.
100%, yeah, garbage in, garbage out. And the SOC analyst is probably in one of the best positions to understand the data going in. And so if they know that they're feeding garbage in, that's going to degrade their trust in the predictions of the model.
Yeah, so we think one of the biggest reasons that machine learning isn't as widely used and trusted in the SOC is that a lot of the methods suffer from a lack of explainability. And without an explanation, it's reasonable for a SOC analyst simply not to trust the machine learning. So again, in the SOC, decisions are being made that have great impacts on organizations. So we want the SOC analyst to have a strong basis behind any decisions being made. So even outside of cybersecurity, there's a general demand for explainability. And one example is the European General Data Protection Regulation, which actually attempts to encode into law the right to an explanation whenever we're dealing with machine learning that tangibly affects people. We also have what's called the National AI Engineering Initiative, and it's being led where Clarence and I come from, the Software Engineering Institute. And one of its core tenets is that user willingness to adopt an AI or ML system is largely predicated on how well they think it is at being both transparent and accountable. But overall, we believe that the SOC analyst has the right to an explanation. So we propose a framework called Cyber-Informed Machine Learning, which is centered on explainability. So there's 3 components to this framework. The first is what we call data to human. And this focuses on what exactly is my data communicating to me. It's the most mature form of explainability in this framework. The second component is model to human explainability. And this is a lesser mature form of explainability. And this focuses on why exactly did my model make a given prediction. And one of the main reasons that we think this form of explainability is so important is that there's a perception that complex models are the end-all be-all for whatever problem you're trying to solve, which isn't necessarily the case. Lastly, we have human-to-model explainability. And this is the least mature form of explainability. And it focuses on the ways that a SOC analyst can tell a machine learning model how they want it to behave, right? So if a SOC analyst keeps getting a bunch of the same type of benign alert, they'd like to be able to tell the model going forward, hey, we can suppress that. You don't have to bother us with that anymore. So we'll cover all of this in more detail as we continue on. We'll provide actionable recommendations for each piece of the framework and opportunities for future research.
Okay, so we'll start out with the most mature type of explainability. This is data to human. And what this is I have a data set and I want to know what the insights are, what valuable aspects of the system, I want to learn from the data some insights about the system that generated the data. And the reason this is the most mature, if you think about it, this is basically the purpose of statistics or more recently data science. It's learning from your data. And so a SOC use case might be, what's my network profile? What does the normal network traffic look like? And so our NetFlow data should be able to tell us this. A more specific use case might be, what's the history of traffic between a particular internal IP and a particular external IP that's on a known suspicious list. While statistics has been around over 100 years, and this type of explainability is mature, we do have some unique cyber-specific challenges that we'll talk through. And so the first one is the prevalence of categorical data. And so here, maybe we have some NetFlow, network traffic features. The first three features, number of packets, number of bytes, and duration, these are numerical features. These are numbers. The last five features, the source IP, the destination IP, source port, destination port, and protocol, these are categorical. So that they may be represented as numbers, but they are not actually numbers. So port 443 is not somehow larger than port 80. And this creates a big problem for machine learning, like really a foundational and fundamental problem, because machine learning and any type of statistical modeling is looking for structure, like mathematical structure and patterns in the data to learn from. And if you just have categorical features, with no sense of scale or sequence, there's not a lot of information to learn from. And so here's just kind of an example to further explain that. The green data points on the left, I think it's pretty clear to everybody that these were generated by some linear function, right? And so we can fit a linear model to these data points, and in this case, it will predict quite well. So now let's consider our NetFlow data. So we have the IP addresses, ports, protocols, and so forth. First of all, how do you even plot those data points, right? It's not clear. There's no natural X and Y position. We'll just represent them as a grid. So each point on the grid represents a flow record. So the question is, what is the underlying generating function here? What function created these NetFlow records? What mathematical model can we fit to these data points? And it's really unclear. It's not clear at all. Because of this issue, cyber data often limit us to basic statistics. So when you think about a lot of the alerts in the SOC, they're simple threshold type alarms. We're really challenged in building models of the relationships between the data points. So this is a big limitation. A second one is related. We call this a weak notion of distance. So when your features are numerical, there's a very natural notion of distance between 2 points. So if we look at the number of packets in a flow, there's a very clear distance between 10 packets and 100 packets that can be quantified. There's no notion of distance between IP addresses or ports. Let's pull this string a little further. We have our two NetFlow logs here with the IPs, ports, protocols, packets, bytes, duration, and type. So there are some approximations that can be used to indicate how similar or how distant or different these logs are. And one way to do that is to simply count up the number of features that share the same value. So here we've highlighted these two records share the same destination IP, port protocol, and type. Okay, so that's a measure of similarity. So let's give this a shot. Let's hand over a set of NetFlow logs to a data scientist or a data analyst. And here, each point represents an individual flow record. And if we just ran unsupervised clustering, for example, we would hope that the clustering returns some type of cyber meaningful groups, okay, that make sense to an end user. So for example, these points up here, maybe they were generated by application number 1, application number 2, the yellow app 3 and app 4. Like this would be great, right? But in reality, this doesn't happen in practice, and this is because of these cyber unique challenges of categorical data and a weak notion of distance. So there are some things that can be done. So Jeff and I are from a research organization, and we're looking at performing research. So this is actually one of the main reasons we're presenting today, is to basically kind of pitch this and just get your feel. You know, is this relevant, and kind of help point us in the right direction here. So one thing that we think can be done is this called cyber-informed machine learning. So instead of me and Jeff as the data scientists alone running the clustering, we get together with the end user and we talk through what they value and what's important to them. And so here they may say, well, ports right off the bat are informative from a network traffic analysis perspective. So maybe we partition the data on ports, and then for each port, so here we have 443, we partition on ingress and egress traffic. And then for each of those bins, we partition on duration of the flow and some type of volumetric, like bytes per packet of the flow. And now we have like cyber meaningful bins in some sense that the SOC analysts can actually relate to. And now we perform the unsupervised clustering, which is shown here. These are the resulting clusters. And these, when they're interpreted, basically give you information about the applications and the users that generate the flow that's in each one of these buckets. So this is cyber-informed machine learning. It's a way of imparting our human expertise into a data-based model.
So now we'll talk a little bit about model-to-human explainability. And one basic SOC use case is, why exactly did an anomaly detector alert to a particular log? This tends to be a difficult question, and it should be worrying that we can't always answer it. So first, a model is explainable if a human can understand the decision-making process behind it. Ideally, machine learning communicates to the SOC analyst how and why a prediction was made, but this isn't usually the case. So we'll look at a couple cyber examples of explainable and unexplainable models. So explainable models are what we call white box models, and they can do things like net flow classification, user and device trust modeling, and email analysis. On the other hand, our unexplainable models are black box models, and they can do things like anomaly detection and deepfake detection. So we'll focus a little bit on the white box models for a second. So white box models are transparent. That means that a human can fully understand the decision-making process from input data to output conclusions. So a SOC analyst will be able to communicate how input data was transformed, how and why a model made a prediction, and what features were most important to that prediction. So if a SOC analyst is working with an anomaly detector, they'll be able to point to influential data points and features to determine whether an alert is benign or not. And this explainable justification is better than just saying, because the model told me to. So one example of a white box model is what's called a decision tree. And they are explainable and transparent because they generate human readable rules that ends up looking like a flow chart. So one question might be, how do we structure a decision tree? Well, the way it works is that we have nodes, which are our features or our variables in the data. And they're connected by logical conditions, which are branches. And so basically a SOC analyst just has to start from the top, answer a bunch of questions, and then they'll reach a leaf node where the model makes a prediction. So given a bunch of network logs, we can actually use a decision tree to classify the log files. So at random, we'll just take, log files have particular statuses. Either they're normal, suspicious, or undetermined. And some of our features include a user ID, a timestamp for when they logged into the network, and a DNS query that they entered. So at random, we'll take row 3 that user 3 logged in at 2:45 in the morning and visited evil.com. And so first we'll ask, is user 3 a verified user? And we answer no. So we come down here. Then we ask, did user 3 log in during a typical workday? And again, we answer no. And then we ask, did user 3 enter a known DNS query? And again, we answer no. So the SOC analyst can see that the model has predicted that we have a suspicious log and we should probably look more into it. What's nice about a decision tree and this visual framework is that a SOC analyst can actually, one, easily communicate these rules to someone else, but they can also prune the tree if there's any information that's not relevant to their organization.
Let me just make a quick comment,
Yeah,
Jeff.
sure.
One thing I think you may be looking at this decision tree and thinking, well, this is really like a gross simplification of what machine learning is. And in a sense it is. This is a very simple and early type of model. Especially when you go on the vendor floor and everything's generative AI and LLMs and so forth. But on Monday, I went to a great presentation by Meta, and they were talking about how they do detecting account compromise by machine learning. And guess what type of model they were using? A decision tree, like one of the oldest and most transparent models. So even though these are simple, I think they can be the most useful.
Yeah, thank you for that. So now we'll take a look at black box models. And black box models are complex models that lack transparency. And that means that a human won't fully understand the decision-making process. So a SOC analyst will know the input data and the model's output, but they won't know how input data was transformed, how and why the model made the prediction, and what features were most important to that prediction. So if a SOC analyst is working with an anomaly detector, there won't be any explainable justification. They'll essentially be saying, because the model told me so. But in all fairness, we have to give black box models their credit. Tools like ChatGPT and just deep neural networks in themselves are routinely producing state-of-the-art results on complex tasks. It's also true that white box models can actually lose their explainability. So when we were working with that decision tree, if you just keep throwing features in and building this decision tree up, eventually it will lose its explainability. We've also seen that there's been a shift towards deep learning approaches on the intrusion detection task. And we actually saw that 5 recent surveys looked each at between 100 to 200 individual papers. So that's on the order of 500 to 1,000 individual papers. And we think this shift towards more complex models on the intrusion detection task suggests that there's some perception that white box models might be insufficient or not complex enough. But that perception isn't always necessarily true. So we have another survey article that actually looked at various white box and black box model performance on both the intrusion detection task and using popular cybersecurity network datasets. And what it shows is that on similar data, white box models actually can compete with black box models. Now, in fairness, we're looking strictly at accuracy here, and that's because in some of these papers, a pairwise comparison was impossible. Some of these papers invented their own metrics, but accuracy was somewhat reliable. But the gist is just that a complex model isn't the end-all, be-all answer to your problem. So actually, complex models sacrifice explainability for an attempt at better performance. And organizations have to decide to either prioritize one or the other, or attempt to find some middle ground between the two.
Okay, and so now we'll go on to our final type of explainability. This is the least mature and where we think the most research is needed. This is human to model explainability. And back to our SOC use case, human to model means the SOC analyst, who's not a data scientist, the SOC analyst wants to explain to the model how he or she thinks it should behave. Okay, so this is a sort of a different direction of explainability. So these are methods that enable end users like the SOC analyst to actually influence the model. One way of doing that, and this was discussed during the meta presentation on account compromise, is through the feature engineering process. And so what feature engineering is doing in this case of categorical variables, like IP addresses, it's doing some type of transformation to convert those features into numbers, because the machine learning requires numbers to learn from. And so there's general ways of doing this, integer, one-hot, and target encoding, for example. What integer does is it just simply assigns a number, an integer, to every IP address, for example. That's nice, but it's also still, it's converting it to a number that the machine learning can interpret as a number, but we're not really imparting any sense of scale or order, or we're not giving it any more information to learn from. We're just converting IP address to an integer. So a cyber-informed way of doing this might be the data scientist getting together with the SOC analyst or whoever the end user is and focus on what's known to be important. So that's identified by the end user, and come up with these transformations that are actually cyber meaningful. So in the case of the IP addresses, instead of converting each IP to a random number, maybe you convert it to a binary 0, 1, 0 if it's an internal IP, 1 if it's an external IP. Or maybe if it's on a known suspicious list, there's a third category. So basically, systematically going through and doing this transformation process in a way that is imparting some cyber knowledge into the pipeline. So our original inspiration for this cyber-informed machine learning came from the engineering field, something called physics-informed machine learning. And this has been under development for the last 10 or 15 years. It's kind of coming to maturity. And it is enabling engineers to incorporate machine learning into things like designing bridges or buildings or industrial systems. So safety critical systems, right? In physics or in engineering space, they have the benefit of governing equations. So I don't know if there's any engineers in the audience, but if so, you may be familiar with like the conservation of mass or the conservation of energy. These are governing equations that the laws of physics actually adhere to, and generally don't misbehave. So like in cyber, one of our challenges is you have actors that misbehave or behave in an unpredictable way. So we don't have that in physics. We have this clean set of equations. These equations are encoded into software models that engineers will use as part of their design process. So if you imagine taking one of these models and running it millions of times over some very large design space, And for each run, you record the inputs and the corresponding output. Now you have a data set that you can use to train a neural network, for example. And now this neural network is mimicking the physics. So this is an example of imparting human knowledge, like our expertise in physics, into a machine learning model, okay? So this is nice, right? But in our case, unlike in physics, we don't have these clean, stable mathematical models. You know, our tech stack is constantly changing. Our users are constantly changing. The threat actors are constantly changing. The TTPs are changing. We will never actually have, you know, stable models like we do in physics. And furthermore, the data that we do have has little mathematical structure, which is what we've talked about. However, we do have sources of cyber knowledge, right, in at least two forms. And the first form, and I think the best form, is our human experts, you know, the cyber analysts or the SOC analysts. They have formal training, they have experience, you know, under the gun, day in and day out, watching traffic, making critical decisions for their organization in a quick way. They have intuition. They have a lot of cyber knowledge embedded in this person. And we also have cyber analytics. And these are basically encoded forms of human knowledge, you know, rules or thresholds that have been extracted, if you will, from a human expert and then encoded into software. So what we need, what Jeff and I propose, is we need formal methods in cybersecurity to elicit this human expertise that we have and that we rely upon almost 100%. You know, that is our source of value, is our human experts. We want to elicit their expertise and then have formal methods to actually put that into the machine learning models. So this is what we're proposing in cyber-informed machine learning. We'll close with a practical example of, you know, what this might look like before our concluding slides. So this is in the context of alert suppression. If our SOC has deployed an anomaly detection model and it's throwing false alarms, you know, all the time, the analyst really needs a way to push a button and to suppress the alerts that they've already pulled the string on and they don't want to hear about again. You know, they know those are benign events. Hit the red button, I don't want to hear that again. So these methods actually don't fully exist. This is like an understudied area of research. One way of going about this might be to leverage something called data poisoning. So this is, in one context, this is like an adversarial machine learning. So how a threat actor may attack your machine learning system by poisoning the training data. Well, if we flip that to our use case, we have an anomaly detection model, and we have data points that we no longer want it to alarm to. If we poison the input data with these benign events that we don't want to see again, there will be some threshold at which the model no longer alarms to those events. And that's what the plot is showing. We did this study with a real cyber data set, and we implemented the poisoning, and this showed basically a threshold of poisoning. In this case, it was around 15% of the training data needed to be poisoned before these alerts could be suppressed. Okay.
Apologies. So now we'll look at some ways that organizations are currently applying or can apply some of these rules. So we believe that overcoming these cyber challenges relies on imparting cyber expertise into the data science pipeline. Some of this is going to resonate at the software vendor level, and some of it might be specific to the organization. So first, on the data to human side, if you take away anything from this talk, the biggest thing that you can do is assign a cyber analyst to work with a data scientist in tandem. You can also develop your own cyber data specialists internally. And lastly, if you have cyber analysts who are interested in data science, provide them opportunities to expand their knowledge. So there's a plethora of free or low-cost training and professional development opportunities. Then on the model to human side, first inquire with your SOC tools vendor whether any of their machine learning tools come with explainability built in. So these tools should at least provide something like feature importances. And again, this is the basically a list of the variables that are most influential to a model's prediction. So one popular tool, it's actually called LIME, like the fruit, and it stands for Local Interpretable Model Agnostic Explanation. And it's an explainability tool that learns a model's underlying behavior by essentially feeding it data and then slightly tweaking that data, almost like a dial, and seeing how that affects the resultant predictions. What's nice about Lime, we're not trying to sell you this or anything, it's open source, but you can feed it black box or white box models and it'll do this for you. Then lastly, you can, if you don't feel like using some external tool, consider working with a data scientist to build your own explainability helper tools. And then for the last piece of the framework, when it comes to human to model explainability, we admit that a lot of research is needed to really develop these methods. But first, consider the benign alerts that got dispositioned in a manual investigation and try to make a structured database with those alerts in it, because in the future you might be able to use that information to calibrate a model. But if you want to do that, you should reach out to your SOC tools vendor and see if they have machine learning features, if they can be calibrated by a human, because that's not always feasible. And again, remember, we're working with SOC analysts, and these people are almost unanimously not data science experts, but we want them to be able to work with these models themselves. Then the last thing you might do is consider talking to a data scientist about the model's retraining policies and see if there's some way to leverage both the data and the retraining policies to reduce the amount of benign alerts going forward.
Okay, and we'll close out with some research needs. On the data to human, really we think there's little needed here. What is needed is transitioning existing research into practice, but I think a lot of these problems have already been solved. Model to human, we need a little bit more work, and the two areas that we see are, one, we can improve the explainability of black box models. So if you have a neural net that is performant, it's performing well, there are things that we can do to improve the explainability, even though it's a black box model. And then the second thing is that we can improve the performance of white box models. Then finally, on the human to model side, this is a more open research question, but we basically need formal methods that allow us to elicit this human cyber expertise and then get that into the machine learning models in meaningful ways. So this is our prepared content. I know it's kind of a quiet group today, last day at a conference, but does anybody have any feedback or ideas, even if it's critical? Well, especially if it's critical, we'd like to hear it.
Very manual process. It almost sounds like it's fine-tuning human
Right. I can repeat your question. So, you're pointing out that this human-to-model explainability has the potential to be a very manual and costly process, and that's definitely true. And so that's, I think, why we need some maybe that could be an aspect of this research, is sort of more efficient methods, because the SOC analysts are already time crunched and they're very valuable. So they're not going to be able to dedicate a large amount of their time to like labeling data so we can put that into the training data sets. But there may be, again, maybe more in research space, maybe there are some things we could do to alleviate this manual effort. Maybe by, this would be operationally, but maybe we start sort of creating a historic repository of their determinations, and then over time we build up a bigger data set of labels that we can impart. There's things like semi-supervised learning that allow you to learn from a large data set, but then provide, like you said, a human in the loop, like a smaller set of like higher quality points that you trust. So maybe the human gives us a small set of labels, but we have methods to somehow increase the value of those labels in the training process. But yeah, I think that's a great point, the potential cost of doing this.
That's a great presentation. One thing I'd like to add, very nicely described the difference between white box and black box models. I'm assuming white box models don't need extensive hardware. For example, often you can just train them and also run them on standard CPUs as well.
Well, yes and no. Let's take the decision tree, for example. Fitting a decision tree is still an NP-hard problem, because when you think about it, the tree as a data structure grows exponentially as you add levels. So it's still compute heavy, especially in cyber, when we may be trying to use big data, like a large historic NetFlow repository. The other aspect is pretty much all machine learning algorithms, even the simple ones like decision trees, use heuristics to do the fitting. And that's because to do the optimal fit is truly an NP-hard problem. So we think there's some research room, in particular on decision trees, for using things like integer programming and linear programming to come up with optimal fits, with lower CPU burden and maybe some more accuracy than heuristics. But yeah, it's a great point. Yeah, thanks.
Good morning. So thank you for the conversation. I'm curious, maybe more of an observation on the human to model aspect. How would we address level of expertise, dissension in opinion about whether or not something really is a false positive or not? And over time, how do you prevent someone in a community or in a SOC from intentionally poisoning the model so that they can take advantage of it later?
Yeah, I mean, great questions. So this could introduce like another type of insider threat potentially, this intentional poisoning of the model. So yeah, I think that's kind of an open question. What was the first part again of your question?
It could be a level of experience or the fact that we're humans, right?
Right.
Thursday, the SOC analyst is in an airport after a long conference, isn't thinking clearly, flags something one way, and then a week or two later says, well, what was I thinking?
Just to minorly jump in, and I'll give it back to you. There should be some sort of like a council or several members. It shouldn't be literally one SOC analyst and one data scientist. There should be people supervising this process and making sure that they can securely validate it as well.
Sure.
And it's a great point too on the uncertainty that's involved in these human judgments. You know, different analysts coming to a different conclusion and how to handle that. So yeah, I think I see this human to model as sort of a two-part process. One is the elicitation process, so eliciting that human expertise. And there are like well-known statistical methods for doing that, like in areas of high uncertainty, you know, where you interview experts. And so maybe there's some opportunity there, but yes, we need to elicit that and somehow handle differences of opinion. And then that's like the first half, and then the second half is once you have it, methods to actually get that into the model, which is also unclear. So yeah, it's a great point.
Great. Thank you.
Thank you.
Hi, thank you guys. Great presentation. And this may speak to my ignorance, but you talked about the ability to take data that's statistical or numerical, but it's harder to make inferences from categorical data, objects. I don't know if is there an approach where these LLMs have gotten really good at, you know, embedding and vectorizing data, open just text, dial down the temperature where they're a little less creative, and maybe dial in the predictions and then combine that with these other models to, I don't know, some kind of a composite model where you're leveraging these really massive LLMs to just get better data predictions that can give you more accurate insights on SOC analysts and even anything in cybersecurity.
Yeah, so yeah, the whole generative AI and LLM space, I think offers a really interesting and powerful sort of a tool here, mainly because we have this sort of conversion, you know, it's natural language, and we're kind of needing to go from natural language of the analyst into something more mathematical that can get into the model. So there may be like some connection there. One of the reasons why LLMs are so large and they require, you know, massive compute is because of this lack of mathematical structure. So like in language, we have the same issue as we do like with IP addresses. You know, one word is not necessarily greater than another word, or there's no sense of sequencing or scale.
It's just token prediction. Yeah, I guess you can't use token prediction in an analytical model to make decisions for an analyst.
Yeah, but I think you've got something there though, because when like you walk on the vendor floor here at RSA, like all of the SOC products are trying to incorporate LLMs. There's value there. So maybe that's a piece of the puzzle that we haven't quite considered.
Great. Thank you.
Yeah,
Thank
thanks.
you.
Hi, thank you for the talk. My question is, when you used that data poisoning, did that affect the accuracy of predictions for other events besides the one that you were targeting at all?
Yeah, so 1 minute. So I guess this will be the final question. Thanks for closing us out. And so in that example, it did actually a little bit affect the accuracy on the other data points. And that is because of the distinguishability between the normal and the anomalous data points. You know, they're not always super distinct. They're kind of mixed together. And I think intuitively that makes sense in cyber. Like a lot of attacks look like normal traffic, or they leverage normal processes. So yeah, that's definitely a key issue that could be part of the research. So yeah, thank you.
Thank you.
So we got the red stop sign. So yeah, really appreciate all your attendance and questions. Thank you. Yeah.